Module 5, Lecture 3. Heteroskedasticity and homoskedasticity only standard errors. Okay, definitions. Homoskedastic. The variance of u conditional on x equaling some value x is equal to sigma squared u, which is constant. This is the point of homoskedasticity, that the variance of u conditional on x is a constant. In other words, the variance of the conditional distribution of u given x does not depend on x. Or we could just write this as the variance equals the variance of u. Doesn't depend on x. Homoskedasticity, it means that the expected value of u conditional on x is equal to x equals 0, or u satisfies least squares number, assumption number 1. The variance of u does not depend on x. So these are the two conditions for homoskedasticity. Heteroskedasticity, it still satisfies the first OLS assumption, the expected value of u conditional on x equals 0, but the variance of u does depend on x. So here, homoskedasticity, variance of u does not depend on x. For heteroskedasticity, the variance of u does depend on x. Okay, let's look at a couple of examples. What do I mean by that? Here we have the average hourly earnings versus years of education. The blue line is our regression line. The black dots are the data points. Now, the question for you is, at each of these values of years of education, does the variance of u, so what are the u's, right? The u's are the difference between each data point and the regression line. Okay, what is the variance? The variance of u. The variance is basically the spread of the u, the spread of the error terms around the regression line. For homoskedastic, the variance of u conditional on x has to be equal to the variance of u. In other words, the variance of u conditional on x, the variance of u doesn't depend on x. You should be asking yourself, does the variance of u in this graph look like it depends on x? Does the spread of these, the error terms, seem like it depends on what's happening on the x-axis? The answer is yes. The variance is much larger out here than it is for smaller values of x. How about this example? Test scores and student-teacher ratios. This one's a little bit less clear, right? So for different levels of student-teacher ratio, the error terms maybe look a little smaller towards the ends there than they do in the middle, but it's really hard to say. So this one might be considered homoskedastic, but it's generally better to always think of your errors as heteroskedastic. There's a really easy fix for this in your regression packages. The problem is that your standard errors are going to be wrong. The whole point of this lecture is that if you estimate a regression and you assume that the errors are homoskedastic when in fact they're heteroskedastic, you get incorrect standard errors. The bad part is that your standard error estimates are too small, and so it makes you reject your null hypothesis more frequently than you should. And the good news is that there's an easy fix to this. So far we've assumed that the UI might be heteroskedastic. We haven't said anything about this. We assume this, but we never explicitly stated it. Recall the least squares assumptions. The expected value of u conditional on x equals 0. In other words, u is uncorrelated with x. xi and yi are IID. They're independently and identically distributed, and large outliers are rare. These two terms we're talking about today concern the variance of u conditional on x. We haven't said anything here about the variance of u. Because we have not explicitly assumed homoskedastic errors, we've implicitly allowed for heteroskedasticity. But what if errors are actually homoskedastic? This leads us to what's called the Gauss-Markov theorem. We can prove that the OLS estimates have the lowest variance among estimators that are linear in y. What does this remind you of? It should remind you of blue, the best linear unbiased estimator. So in the context of ordinary least squares or OLS, this is called the Gauss-Markov theorem. In other words, OLS is blue when some assumptions hold. The formula for the variance of beta hat 1 or under homoskedasticity is given by the following. So variance of beta hat 1 is equal to the variance of x and u, x multiplied by u essentially, over n times sigma squared x, or the variance, this bit right here is just the variance of x, and we're going to square it and multiply by n. So we can put the definition of the variance in here, so that's going to be the expected value. We're going to this step here, the expected value of x minus its mean squared. So we're just swapping out the variance, the definition of variance here, and we have ui squared. And then we can distribute the expectation because we're assuming homoskedasticity, which means the variance of u does not depend on x. And so we can easily just distribute this expectation through, and we get the expected value of x minus its mean squared times expected value of ui squared over what we already talked about. And so this bit is again just the variance of x, and so that's what we write here. And this bit is the variance of u. Why is that the variance of u, you might be asking yourself? Okay, so remember, by OLS assumption number 1, we're assuming the expected value of u is equal to 0. And so when we take the variance, we're just subtracting the mean, right? We're going ui minus its mean, mu u, squared, right? And so since by assumption, or actually by construction, the expected value of ui is 0, that part drops out, and we're left with expected value of ui squared. Okay, then going back to our steps here, we have a squared variance on the bottom, so these two cancel out, and we're left with this formula here. So the variance of beta hat 1, when errors are considered homoskedastic, is just the variance of u over the variance of x times n. So the homoskedasticity only standard error formula, so the previous slide was the population variance, now we're talking about the standard errors. For homoskedastic, we get this, so we're just plugging in the sample analog of what was on the previous slide, the estimator of the variance of u over the estimator of the variance of x. Notice we have some degrees of freedom corrections here. That we compare this to the non-homoskedastic case or the heteroskedasticity case. We need to add back in this part here, the variance of x again, because we couldn't make that step in the previous slide where we distributed the expected value, so this part has to stay, and we can't cancel out an extra squared term, or an extra variance of x term. In general, you should always estimate heteroskedastic robust standard errors, again, because it's basically impossible to know if your errors are homoskedastic, and it doesn't hurt to estimate heteroskedastic robust standard errors. The nice thing is that R in any statistical package will just estimate these formulas for you. You just have to specify which one you wanted to estimate. Note that if we were doing this in Excel, you would always get this standard error formula, when in fact you want this one. That's one benefit of using R. Okay, so the Gauss-Markov theorem assumptions. These should look familiar, the first three. The expected value of u conditional on x is equal to 0. Xi and yi are IID. Large outliers are rare. But now we're adding u is homoskedastic and u is distributed normal with mean 0 and variance sigma squared. These assumptions are more restrictive, but they allow us to use simplified versions of statistical tests. In other words, they allow us to apply the central limit theorem and use standard t-stats and p-values. They're more restrictive in the sense that there's more of them. We're adding 4 and 5. Under OLS assumptions number 1 through 4, beta hat has the smallest variance among all linear estimators. In other words, it's the most efficient amongst all linear estimators. Under all 5 assumptions, beta hat has the smallest variance of all consistent estimators, linear or nonlinear functions of y I through yn, as n goes to infinity. So if it's a consistent estimator, if we're getting if as n goes to infinity, we get closer and closer to the true population value of beta 1, then OLS has the smallest variance if all 5 of these assumptions hold. In other words, OLS is a better choice than any other consistent estimator, and because an estimator that isn't consistent is a poorer choice, this says that OLS really is the best you can do if all 5 extended least squares assumptions hold. Okay, so don't get too excited yet. The Gauss-Markov theorem isn't that compelling in practice. We already saw the 2 data sets in the beginning of this condition. If we condition on homoskedasticity, the condition of homoskedasticity isn't always likely. Results only hold for linear estimators. There's many other non-linear estimators that might be better. And the strongest optimality results requires homoskedastic and normal errors. What does this all mean? Inference if U is homoskedastic is normal and easy. We should also note that if you just implement the heteroskedastic error formula in R, then inference is also easy. We're back to the same situation. We just correct our standard errors and we have the same old t-stats that we did before. Nothing really changes as long as you tell R you want heteroskedastic robust standard errors. And this means we can rely on the central limit theorem to perform hypothesis tests because our betas are normally distributed. So the bottom line takeaway for this is just always estimate heteroskedastic robust standard errors.